Hi guys, welcome to lesson 2.5 on modeling direct variation. Modeling direct variation is another way we talk about linear equations. Last section we talked about the idea of y equals mx plus b, where y equals mx plus b is a linear equation. We use this as slope-intercept. Okay, so slope-intercept form says y equals mx plus b. And remember, in slope-intercept form, b is the y-intercept. This is the point at which the graph crosses the y-axis. All right? And so with that said then, we're going to talk a little bit about y-intercept and what that means in a direct variation. All right? And so the first thing that we're going to talk about today is we're going to talk about a definition of direct variation. The definition of direct variation is an equation of the form y equals ax. And that represents and I'm just going to abbreviate dv, a direct variation between x and y. Okay? So an equation of the form y equals ax represents a direct variation between x and y. And the constant of variation is the a, all right? The non-zero constant a in the form y equals ax, all right? So when we start talking about direct variation, you'll notice that direct variations are in the form y equal ax, which looks an awful lot like slope-intercept form, but the big difference here is that there is no number here on the end. All right, and so as we get into this idea of direct variation, I want you to recognize the fact that a direct variation is exactly like a slope-intercept form equation. The only difference is there is no y-intercept. Well, what does that mean when there is no y-intercept? It means that the y-intercept, or the value of b, is equal to 0. All right, so you can kind of hold on to that thought for just a moment, and let's see what we can come up with in these boxes down below. First of all, a direct variation in its equation form is y equals ax, which we already talked about, represents a direct variation between x and y, and is said to vary directly. Y is said to vary directly with x. The non-zero constant a is called the constant of variation. The graph of a direct variation, y equals ax, is a line with a slope of a and a y-intercept of 0. Once again, if we take y equals mx plus b, and we use a slope of a, and we use a y-intercept of 0, then we get the equation y equals ax. So essentially, a direct variation equation is a line with a slope of a and a y-intercept of 0. The family of direct variation graphs consists of all the lines that pass through the origin, because once again, b is equal to 0. So a couple examples of direct variations. Y equals 1/2 x. Okay, says that y varies directly with x, and the constant of variation is 1/2. In this case, the constant of variation is -1. And so if the constant of variation is negative, that means you're going to get a negative slope, so the line will fall as you go from left to right. If the constant of variation is positive, then it's going to rise from left to right. But the key ingredient here is that both of these have a y-intercept of 0. So let's take a look at writing and graphing an equation that has -3, 2 as a solution. -3, 2 is up here. Right, here's -3, 2. So it's left 3 and up 2. And we know that every single direct variation has got to go through the origin. Now, use a straight edge when you do yours, but it goes through that point there. Now, the text is going to tell you to do it this way. They're going to say, go ahead and plug in the values of x and y. So we're going to substitute 2 for y and -3 for x. We're going to go back and put that stuff in. And so again, x is -3. Divide both sides by -3, because again, -3 and 2 are the given values of x and y. And so a is equal to -2/3. So my variation equation, direct variation equation, is y equals -2/3 x. Now, if we have a picture, we can also use a little common sense here and say, well, remember that a direct variation equation is just simply y equals mx plus b, where b is 0. And then if we could find the slope from the picture, it's just down 2/3. So down 2/3. So my ratio is rise -2, run 3. And then we just get rid of this part, and there's your equation. So whichever way you like, it's perfectly fine. Why don't you guys try the checkpoint problem at the top of the next page here, and let's see how this goes. We'll be back to go ahead and go over that example. All right, so we're going to write and graph a direct variation equation that has the ordered pair 4, -2. So first we're going to graph 1, 2, 3, 4. 1, 2, 3, 4, and -2. There's that point right there. There's 4, -2. And if you like the method I finished with last time, we can simply say we're going to go connect those 2 points with a line, because again, I know that my direct variation, since it's a direct variation, it has to go through the origin. So it's down 2 over 4. And so my slope is down 2 over 4, which is the same as -1/2. So my direct variation is y equals -1/2 x. So that's one way to do it. The other way to do it is to take my equation, my standard form of a direct variation equation, y equals ax, and plug in x and y and solve for a. So y is -2 equals a times x. Divide both sides by 4. You get a equals -2/4, which is -1/2. Once you know that a is -1/2, you have your equation. So whichever way you like is perfectly fine. All right, our next idea then is going to get into this applying a model for direct variation. So we're going to talk a little bit about Hooke's law. Hooke's law is basically talks about spring constants. So it's kind of a physics application. It says, according to Hooke's law, the force that is needed to stretch a spring varies directly with the amount of spring stretched. So the length of the string that's being stretched is going to vary directly with the force. All right. If 64 pounds of force F stretches a spring a distance of 8 inches, write an equation that relates F and D. Predict the amount of force that's needed to stretch the spring 14 inches. So let's deal first with part A. For part A, because it is a very directly problem, because it talks about varies directly, we know that the force varies directly with the amount of spring. So force is going to vary directly with the amount of spring, which they use as D, being the distance or the length of the string. So we've written our direct variation equation. Now let's plug in the information that we have. We have 64 pounds of force. We don't know our variation, our constant variation, but we do know the length of the spring is 8 inches. Divide both sides by 8. And so for this particular style of spring, the constant of variation is 8. Don't worry about the actual units for that. It should be pounds per inch, but that's not a big deal. We won't worry about the units right now. So we're going to substitute 64 for F and 8 for D. And again, by dividing both sides by 8, you get 8, because 8 times 8 is 64. So the equation that relates F and D is F equals 8D. So to stretch the spring 14 inches, we want to plug in our constant of variation, which is 8, and our D, which is 14. And then we're going to go ahead and we're going to get that calculation, and 14 times 8 comes out to 112 pounds of force. So that means we need 112 pounds of force to stretch that spring 14 inches. Okay? All right, so another checkpoint example here. Why don't you guys go ahead and give that one a shot and restart the video and let's see how it goes. All right, so we're going to use the exact same equation this time. Again, force is equal to 8D. This time they're going to give us the force, and we have to solve for the distance, predict how far the spring is being stretched. So we're simply going to plug in 92 equals 8D, divide both sides by 8, and my new length of string must have been 11.5 inches. All right, since it's a stored problem, make sure you have units with your answer. All right. Finally, on the last page here, we're going to talk a little bit about using ratios to identify direct variation. Now, if the value of x and y vary directly, that means that if I write my constant, my direct variation equation, y equals ax, I can divide both sides of this thing by x and solve for a. And so the constant of variation is always y over x. All right? And if these two quantities are set to vary directly, then we can always divide the value of y by the value of x and get my constant of variation. So having said that, it says the table below gives a sample cell phone bill showing the total monthly cost and the number of minutes used that month. Tell whether the total cost and the number of minutes show direct variation. If so, write an equation that relates the quantities. So what we have to do then is we have a cost, and our cost is dependent upon the number of minutes. So my number of minutes is my x and my cost is y. And so we're going to then divide and do a ratio of cost per month to see if that cost per month is constant. If it is, then the two quantities vary directly. If it's not, then they don't. So in the first example, it's $35, okay, for 100 minutes, and 35 over 100 comes out to 0.35. In the second month, it is $45 for 129 minutes, which is roughly 0.35. Rounded off, but it's pretty close. And then 80 divided by 229 comes out to about 0.35. $15 for the fourth month, okay, and 44 minutes, that comes out to about 0.34. And so it doesn't vary exactly. We can't say that it varies directly with exactly, but we can write an approximate direct variation equation with this situation, because in this case you can see that y varies with x directly with a ratio of about 0.35. So since the cost per month is about 0.35, which comes out to be dollars per minute, so about 35 cents a minute, then the cost is equal to 0.35 m. And so we write our direct variation equation. Again, we've verified that it is a direct variation by calculating each constant of variation for each data point and making sure that those values do in fact vary directly. If we would have gotten something like 0.85 here, let me undo that. Let's do a different color. Suppose we did the same problem, we got 0.85 here and 0.45 here and 0.76 here. Now we could not say that they vary directly, so for this problem we would say it does not vary directly. All right? Okay, so last checkpoint problem. Let you guys try this one. We'll be right back to go over your results. All right, so if x varies with y, that says that a is going to be y over x. Once again, taking the equation y equals ax, divide both sides by x, we can solve for a, and so a is equal to the ratio of y over x. If those two quantities, the ratio of y over x, is constant, then we can say that this does vary directly. So let's go ahead and start dividing. Let's do -2 over -1, which is 2. Let's do 2 over 1, which is 2. 6 over 3, 2. 10 over 5, 2. 14 over 7, 2. And so you guys can see from the table that basically the y values are twice as much as the x values, including this -1, where it's -1 doubled, we get -2. So y is equal to 2x, because my constant of variation is 2, and y varies directly with x with a variation constant of 2. All right, so that really concludes direct variation. Again, remember, direct variation is a very simple way to talk about linear equations. The only main difference between a linear equation, y equals mx plus b, and a direct variation equation is the fact that the b, in this case, is always equal to 0.